I will briefly introduce a little bit about myself. I'm a data scientist at Jon Snow Labs, and I've been working with natural language processing, most of it, both in academia during my master's and part of my PhD, and in industry by building solutions and consultancy services for many different domains, including healthcare, finance, and legal. Okay, today I will talk about automatic speech recognition, and I will focus a little bit on a brief introduction of the topic, and I will show how we can use that using Spark NLP, which is an open source library that you can use in Scala or Python. So I will go on, and please feel free to interrupt me and make questions. Please don't need to wait until the end of the presentation. I will, from time to time, check on the Q&A section to see if there is some questions over there, so feel free. So for those of you who are not familiar, when we are talking about automatic speech recognition, basically we are talking about understanding audio. So we get an audio input, which is this wave over there, and then how can we use computers to automatically process this input and hopefully understand it very well. So I put an interrogation mark because there are many different things that you can do with audio. And for example, you can do voice dialing, which is basically what Siri and all of those assistants, they do. So you can give commands to some computer, and it understands the command and takes some action. So you can turn on and off your lights at home, you can make a call, or maybe you can just ask for it if there is cheese at your refrigerator and things like that. So you can just ask for a command and the computer will understand and knows what to do. So the focus of today's talk will be on this orange part of the presentation, which is how to transform audio into text. So we want to create a text representation of the audio. So this is usually done on YouTube, then you can create automatic captions for videos, and those big companies, they can achieve very good results with automatic caption. Other things that you can do is to analyze the audio. For example, you can analyze the voice of people talking and take some classification into emotions. So you can check if your customer, for example, is very angry at your product, or maybe he's very happy, and you can take some action accordingly. So this is important for many different applications, and there is lots of research that are using both the audio and visual inputs to take an even better solution on identifying emotions. So you can take facial recognition, or maybe you can body language to detect if the person is in some classification of emotions or something like this. And also, it's important to be able to distinguish between different voices. So there are some applications that you can use to unlock doors, for example, but you don't want the door to be unlocked if it's not you who is giving the command to unlock the door. So how can we distinguish people by getting their voice input? And of course, there is also other things that you can do. Those are just 4 examples that are very well researched. So I will go over a brief history of automatic speech recognition, just to say that it's a long history, and it started in the 50s when we have many mathematical models to identify and to the audio and have some understanding of it. So it started with the Bell Laboratories. They had an Audrey model that was able to identify digits. So you could say a phone number, and the system would be able to identify the numbers that you were saying. Later on, IBM released Shoebox in '61, and it was a little bit better. It was able to recognize numbers, but also make some math between the numbers. So you could do some addition of the numbers, subtraction, multiplication, and division. So it was an improvement over Bell Laboratories Audrey, and it was already something interesting. Later on, in '76, we have Carnegie Mellon University releasing a system called Harpy, which was already able to identify much more words, not only digits, so up to 1,000 words. And in the '90s, the Dragon Dictate. If you are close to my age, you should maybe even tested the app to dictate, and it will be writing what you were saying. Later on, it was bought by the other companies. And this was already very, very robust solution in the '90s. Was able to identify 80,000 words in the dictionary. So it was already production ready solution. And what we are more familiar with are the most recent advances, which are made mostly by the big tech companies. And we have Google Voice Search, for example, that they were already using much more complex models based on neural networks. That was a big improvement in terms of accuracy of ASR systems. And later on, we already have lots of cloud solutions that are available for all the big tech companies that you can use their API services or the cloud services to provide solutions for many applications. And after the 2020s, we are seeing the new models. They are based on transformers. Since transformers, they were initially designed for text, but they are being adapted to many other fields, and audio is also one of them. And the two models that we will talk a little bit more today, they are the Wave to Vec and the Hubert models. They use transformers in part of them. So it is important to know that those models right now are achieving state-of-the-art results on all the benchmarks. And you can see there are some dashed lines here that I'm just pointing out why we had some advancements in the field since the release of HMMs, the hidden Markov models. We got huge improvements in the models by transitioning from pure mathematical or statistical models into a probabilistic one. It was able to achieve, I believe, if I'm not mistaken, it was more than 30% improvement or more than 40% improvement just by changing how you model your data. And then LSTM, which was a big improvement specifically for audio also because of the long sequences. And there were a lot of problems due to vanilla RNN cells. They were getting into the vanishing gradient problems or exploding gradient problems. So LSTM fixed that, and they were able to process longer sequences, and we got a huge improvement in the models, as we could see in Google Voice Search, for example. And later on, 2017, transformers, as I mentioned. And just one extra comment, which is, of course, at the beginning, in the early days, we have very small data sets available. So it was very difficult to train bigger models, and all the applications of the systems, they were person dependent. So this means that you can say your phone number for the system to identify the digits, but before that you need to make some training by speaking some predetermined sentences so that the system could adapt to your voice, and it would be person dependent after that. And later on with the HMMs and deep neural networks, it's not person dependent anymore. You can identify words even if is being said by different people. And now we are already have much more training data available, especially for English and other widely researched languages like European languages. So what are the main difficulties when modeling audio? So the problems are, it's very hard to differentiate the audio inputs, even if they are saying the exact same thing. So in a text, you would have one sentence independently to who is speaking the sentence, independently of how fast or how slow you are speaking, or if you have background noises, or if there are other people speaking behind you, if you have accent like I have. I'm not an English native speaker. So all of those nuances of the language, they affect the quality of your models. And this doesn't happen when you have text. So audio is much more complex. Also, in some cases, especially in research, you train your models on clean data, pre-processed data. But when you try to apply your model, you don't have the exact same conditions. And sometimes your model doesn't show the same metrics or the same performance as you were expecting. And for a modeling perspective, it's a very hard problem to solve because we have a high dimensionality for the classification of your outputs, and you usually have very long sequences of the audio input. So these long sequences is known to be a hard problem even for deep neural networks to solve. So just to give a small examples for different languages, how many phonemes they have. So the top one that I could find is Hindi, which had 49 phonemes, and the one with the fewer number of phonemes is Hawaiian, and we have a very different numbers of phonemes per language. So it's interesting to see that, for example, English, it has 44 phonemes and is a very high value, but other languages like Spanish, it only has 24, and it should be probably easier for a model to learn ASR model for Spanish than English in theory. Well, of course, we have much more data available in English. A brief evolution of the models. At the beginning, we have trying to identify the phonemes given the audios. So this was a very hard problem, and those language and nuances were very, very impactful on those models. Then we started using probabilistic modeling, and we divided the problem in two. So we have an audio model and a language model separated, that they were training separately, and then they were joining by some techniques on how to process them, but they were basically two different models. And now what we have is an end-to-end approach that we can use deep neural networks from the beginning to the end. So we have the audio input. It's automatically learning features of the audios and together learning features from the text. And they perform the translation from audio to text out in just one model. So Wave2Vec and Hubert, they are both an end-to-end solution for this. They are on the most recent models. So how they, in a very summary view of it, they are just learning two things at the same time, and what they do is they try to align the texts with the audio. So in one side, you have the audio that will be processed, and they will extract features from the audio, and they will create an audio representation. And on the other side, you have the text, and you will have embeddings and learning representation and transformers even for masked learning. And then you will have the final output that will take both the audio representations and the text representation into account. And you make predictions using a decoder like beam search or Viterbi. So for Wave2Vec and Hubert models, they are basically in this architecture. You have the audio input at the bottom. It will be processed and create audio features using usually CNNs, like 6 or 7 layers of CNNs. And then you will also process the text using transformers-based embeddings and training with in a masked language model. And the audio representation will be also included in the processing. And then you have the output of your model, and you will use some kind of loss function. So Wave2Vec and Hubert uses different loss functions. We'll see it in the next slide. So basically, Wave2Vec use CTC and diversity losses to account for the sequence of the sentence, and to give extra points but for diversity. So you will not get too much repeated words or too much repeated characters or phonemes out of your model. In the other hand, Hubert uses cross entropy loss function that is the same as the BERT original paper used, and some people say that this makes the training easier for this model. One big difference between Wave2Vec and Hubert is that Wave2Vec, it uses a sampling to generate candidates of the phonemes using softmax approach, while Hubert, it will first cluster the audio features extracted from the audio input using k-means, and also by transforming the audio into a better representation using MFCCs. So those are the biggest difference between Wave2Vec and Hubert, and also Hubert uses the BERT directly for creating the candidate phonemes that will be selected with the beam search algorithm. So how can we measure accuracy of these kind of systems? So word error rate is the most widely used metric. So it takes into account basically what you had wrong divided by the number of words. So you have a rate of between 0 and in theory infinity, because you can insert lots of words into your transcript and get lots of numbers in the numerator. But as close to 0 as this rate goes, the better your model is. So it means that you are correctly identifying the words by transcribing it. And just to explain the formula, it's very simple. SUB means substitutions. So if you speak one word, but the system transcribed a different word or a word with spelling errors or something, it will be a substitution. And if the system inserted a new word that was not present, it is insertion, and deletion the same if it's deleted from the transcript. So this is a very simple mathematical formula. You just sum what you did wrong and divide by the total, and you will get a rate between 0 and some number, and then you check how well you did. So what are the different data sets that we have? So the most widely used in research benchmarks is the Libre speech, which is available to download and use it. And it's a good baseline to test ASR models. So the data set consists of audiobooks. They are narrated by different people, and they contain lots of training hours. So other interesting data sets are Common Voice and Vox Populi. And also we can see some specific for finance that you can, for example, the earning calls, when you can the narrators, they are explaining metrics and KPIs and other finance related content, and you can use this data set to understand or make automatic analysis or different approaches for finance. So there are probably more data sets. This is just some of them, and probably all the big companies, they have their own data sets that should be bigger, most probably, and curated also. Okay, so now I would just make a brief introduction to Spark NLP, and then I will show you how to use the code to use Wave2Vec or Hubert to make translation from audio to text, so speech to text or ASR. So if you're not familiar, Spark NLP is an open source library. It's built on top of Apache Spark and Spark machine learning library. So it contains all the usual NLP tasks, and is the most widely used in the industry for NLP. And we have licensed versions of the library that are specifically to attack problems in healthcare, finance, and legal, using pre-trained models or other NLP tasks that are specific for those domains. So the Spark NLP is open source, and it contains lots of NLP functionalities. It works in pipelines. So as you can see in the image, you start with the raw text, and then you start to build up what we call annotations, which contain the information and metadata of each step. So document assembler creates a document type of annotation that will contain the text information and some metadata. The same for tokenizer, which will split the text into tokens and will add extra metadata. And so on. For each of the steps, we have many different annotators that we call them, and we can start building different pipelines to perform many tasks in parallel. So usually we have two main types of annotators. So one is annotator model that is able to use pre-trained models that are freely available on NLP Models Hub. So we have many pre-trained models for many different languages. For example, the model for NER. So NER model is the name of the annotator, and you can use many pre-trained NER models to tackle different entities and different problems. And the other type of the annotator is the approach, which is the one that is used to train new custom models. It is compatible to GPU because it uses TensorFlow in the backend, and it's just change model by approach in the name of the annotator. So this is an example of a pipeline that we can create. In this pipeline, we start with document assembler, which is the first initial step to transform raw text into annotation. And then we go on to tokenize, create embeddings, and identify entities. So if you're familiar with PySpark and Spark machine learning, you are familiar with the pipeline that you can give each of the steps. And then you can just use it on new data. So this is the first page of NLP Models Hub. So we have more than 100 annotator classes because we have implemented many different transformer-based architectures, BERT, Albert, Alberta, Roberta, and so on. And we have all of the NLP tasks that you can think of for classification, dependency parsing, stop word cleaning, word segmentation for Asian languages that don't have white space between words, and so on. And of course, we also have automatic speech recognition. So for automatic speech recognition, how to use it, we don't have the approach annotator to train a new custom model, but we have the pre-trained models. So for Wave2Vec, which was implemented in September last year, we already have more than 2,000 pre-trained models. And for Hubert, it was implemented in February this year, so we only have one model pre-trained. And of course, we can add more models because we can migrate models from Hugging Face to Spark NLP. So this is how we usually do. We identify interesting models, and then we can migrate them to Spark NLP. So how to use the code? You just use the name of the annotator, for example, Wave2Vec2 for CTC. And then we use the pre-trained method and give the name of a model that will be automatically downloaded from Models Hub. And then we need to set input columns and output columns. So for those annotators, we only have one input column, which is the audio, and one output column, which will be the text. So they have different names, different architectures, but they work in the exactly same way when using Spark NLP. So if you want to learn more about Spark NLP, you can check all of those links. I think we can share the presentation afterwards, and you can just follow all of the official documentations about Spark NLP. And one thing that is interesting to mention is that we do trainings and certifications. So if you are interested in learning how to use Spark NLP for data science, you can check all of those links. Okay, so let's make one example. I will just quickly check if there is Q&A. I don't see any red number on it, so no questions. I see something on the chat. Okay, so the example that I wanted to share, I will put them on the presentation. But if you are interested, I can show how to use the code. Also, just share it a little bit. So what we are going to do is we need to create the pipeline. So the pipeline, it will pre-process audio files, and then it will create the pipeline with 2 steps only, 2 stages, and then we can use this pipeline to extract the text from those audios. So basically, what we need to do is first read the audio file into an array of numbers. So we use the librosa for that, and it's very easy to read, and just librosa.load, you give the file path, and then you can change the sampling rate of this file. So the usual sampling rate is 16,000, and of course, the higher the number, the more accurate or the more high quality is the audio, like CDs are 48,000 and so on. But for research and for ASR systems, this is the number that is usually used, 16,000. And in Spark NLP, we are not supporting at this time NumPy float 32 number type, so we just send this NumPy array returned by librosa, and we just transform it to a standard Python list with float values. So then we create a PySpark data frame. So I know that this code can be confusing if you're not familiar with PySpark, but it's just a way of constructing data frames in Spark. So we use Spark to process data so that we can easily scale to process big data. So process lots of data at once. I'm just checking some questions. So what is the typical word error rate for finance and healthcare? So it changed a lot. We don't have any accurate measure for finance and healthcare. We do have some models, I believe, that were trained for finance that if I remember correctly, they achieved like 15% word error rate on that earning calls data set. If I'm not mistaken, it was around 15 to 20, if I'm not mistaken. For healthcare, it can change a lot depending on which application. So just to give an idea, all of those new models that they achieve state of the art right now, they are still getting around 10% or 8% WER on the data set. And this means that we still didn't achieve more than human capability with the model. So there is still lots of improvements to do. So human error rate, I think it's around 4% or 3% word error rate. It's much slower than the models can do right now. So the next question is the process of fine-tuning models similar to Spark NLP pre-trained models? Is there a learning curve as newer models became available? So for this second question, the process of fine-tuning the Hugging Face models is done outside of Spark NLP at this moment. So our annotators, what we can do is to get the final version of the model and transform it in a format that is compatible with Spark NLP. So what we actually do for these two specific models is just reformat them and migrate to Spark NLP so that we can easily use on our pipelines. So the process to fine tune, I do have one reference link at the end of the presentation that tells you how to fine tune Hugging Face model. And you can check that link later. And if there is a learning curve as newer models become available, well, if there is a breaking new technology or new architecture, there is a learning curve, yes, but it depends on how you use. So if you are in research, you will probably need to go into detail on how the model actually works, understand the math behind it, and understand each step of the model, which can be very complicated. But if you are in the application side of the artificial intelligence, those models will probably be implemented in some libraries like PyTorch or available on Hugging Face, available in Spark NLP. So you can just use the same classes, the same libraries, the same packages, and use them probably in a very similar way as you did in the others. And I would just show again how to use in Spark NLP. Those they are exactly the same. So basically just change the name of the class or the name of the annotator that you want to use, but all the other parameters and all the other concepts are the same. So you need an input as an audio and output a text. So maybe a new model will not only have an audio as input, but maybe other features coming from something new. So you would just have the input columns as an array with more than one item. So you will have the audio assembler or maybe the text assembler also that you would use as input. So those kind of learning curve in libraries, in packages, is not so high. But if you are in research and if you want to understand deeply how the model works, so it can be very high learning curve. Do you have multilingual or bilingual ISR models? Yes, we have. We do have 2,616 pre-trained models. And we do have for different languages, and we do have some of them for multilingual. If I'm not mistaken, we have multilingual. I can check later on, but I've seen some of them work on, I'm not sure if it's completely different languages or if they were trained on the non-native accent for English. For example, they can understand English from England, from United States, from South Africa and Australia, and non-native speakers and all of that. So, but I do believe out of those 2,600 models, some of them can be bilingual. Okay, coming back to the implementation. So we have the data frame. So we create this schema. Is just saying that we have the audio content, which is that what we got on the previous step, just this one, this data, which is a list of float numbers. So it's an array type of a float type, and we have the sampling rate, which is just a number. So in this case, we have 16,000 as a number. And then we will create the data frame with these two columns. And this is how we can create in Spark. So Spark here is a Spark session that was initialized before. So we have some Spark cluster running, and we create data frame in this cluster. So the upside of using Spark NLP is that you can easily scale because you are building on top of Spark. And then we can just create the pipeline. Pipeline will have two steps or two stages, which is the audio assembler, which will get this list of float numbers and create an audio type annotation. So this annotation will have this list of float numbers, but it will also have some extra metadata from it. And then we can use, in this example, Hubert for CTC. And then this is the only model that we have at this moment. And we will have as input the audio assembler of the previous stage. And we will output the transcription of the audio. Then we can define the pipeline with these two stages. We'll just quickly check the questions. What is the performance of this library? How many audio channels can be processed with latency less than 1 second? Say one AWS server with 4 NVIDIA T4 cards. So I don't know how to answer this question. I've never tested for latency for these specific annotators. What I can say is that as usually in Spark, it can be very resource demanding. So we usually ask for at least 32, we recommend 64 RAM memory to process the pipelines. And of course, the more clusters and the bigger your server, the better the latency. But I don't know. We don't have the benchmark for specific numbers of latency if it has less than 1 second. We don't have those numbers. And how are these different to commercially available products as well as OpenAI Whisper? Okay, so the difference is that this is a tool to build those commercially available products. So Spark NLP is an open source library to work with NLP. So we don't have the production ready solution as the Whisper or as the Google Speech or the Microsoft Azure Cognition for speech and so on. We don't have the production ready solution. We do have the models. So we have the models and you can use them to build those type of products. And what platform do you train these models on? What does it cost? So for these specific models, for automatic speech recognition, we currently don't have the approach type annotator, which is the one used for training. So we are not capable at this moment to train new custom ASR models. We can only import them from different sources, TensorFlow Hub or from Hugging Face. For other annotators, we can train them on any server that you wish, or even locally, depending on the size of your data, of your on the demand that you may have on the infrastructure that you need. So for many NER models, for example, I train them on my computer. Some of them can fit on Google Colab, depending on the amount of data. And we do have Jon Snow Labs, some development servers that have GPUs available and so on. Okay, so the final step is just to first have a model class. Again, if you're not familiar with Spark ML, this is the pipeline is a pipeline. It's not a model, and we need to fit it on data so that you will obtain the pipeline model that can be used for predictions. So this step is just a formality. We need to fit it to obtain the correct class. But since in our data, we only have pre-trained models, it's not performing any training. It's just transforming the classes actually. And then using the transform method, we can make the predictions. So the predictions, we can see here, and we can check, we can listen. Let me see if you can. I'm sharing my sound. Please let me know if you can listen to it.
For a little bit history of Wave2Vec 2. Wave2Vec 2 is one of the current state-of-the-art models for automatic speech recognition due to self-supervised training, which is quite a new.
Oh, are you able to listen to it?
Yes, we heard it.
Okay, perfect. So basically, we can see many problems with the transcription, but overall, you can understand very well what the person is saying. So this audio I took from one of the webinars from Jon Snow Labs. This is my colleague talking, and we can see some interesting points, which are technical words. They are harder much harder. The model is not able to understand Wave2Vec 2, for example, and you have many errors on here. And Spark NLP, for example, the model is not able to understand that because it's probably not present in the vocabulary of the decoder, and is very technical, so the model didn't learn those words. And different other types of error which can occur. This is part of how the decoding system works, is to remove duplicated words. So if you have weak, sometimes it transforms into whack. So this is usual errors that you may have on speech recognition tasks. Also, of course, a speech recognition, sometimes they just make it wrong. So you get some wrong transcriptions, but overall, the text is very understandable.
New concept in this field, using 1 hour by little.
So since we are using Spark NLP, we have text that was extracted from the audio. We can use all of those 100 annotators and perform additional analysis. I would just show how to use context spell checker so that we can try to correct or try to fix some of the mistakes that were done and maybe have a better model. So what we do is, since we have the text available, we just create the tokenizer to split the text into tokens, and the spell checker model. We have many pre-trained models for different languages. So the standard one is for English, and it also takes into account the context. So it's based on deep learning. This model, we have other dictionary and rule-based spell checkers also. So we just create a new pipeline. We have the tokenizer and the spell checker, and then we just can fit in an empty data frame just to have the model. So then we can just transform the previous result, and we can collect the tokens. Since the spell checker returns tokens, we concatenate them with white space between them. And we can see that the models were able to correct some of the usual words that we have, like the weak, it corrected, it fixed the current, the addings, and so on. So it was able to improve a little bit the word error rate, right? So we already got like 4 or 5 extra points here just by passing it to a spell checker. Yeah, so some of the questions, the problem is not technical words, but proper nouns or names. Yeah, proper nouns or names, they are also a problem for many language models. And of course, technical words, when I say that, is because it's probably not present in the training data. So this model, it was trained on the audiobooks. So I don't think there was any audiobook about Wave2Vec or about Spark NLP or even Spark present in the training data. So that's one of the reasons why technical words, they sometimes don't work very well on pre-trained models. And of course, if you are using this model in a very technical application, you should train your model using those a vocabulary and using training data that has technical words on it, so that the model will be better prepared for those. And acronyms also is also a problem, but there are some techniques to try to deal with that. Nice that the cursor helps. I also like to be following with the cursor. Okay. Okay, so let's put them side by side. So the blue dot, it is the original sentence, and the yellow one is the sentence after spell checking. And we can see that we were able to fix some of those problems. As on the red words, you can see them. So this was just one example. I took an audio file that was not present in the training data, and we can see that the result sentences are not so bad. We do have lots of errors, but overall, if you are listening to the video and reading this audio, this automatic caption that was created, you could probably follow easily on the video. Okay, so I'm just giving some extra links. So some documentation from John's Law Labs, and also some nice blog posts and documentation and papers and so on that I thought was very useful for reading about automatic speech recognition. Some of them are very technical, like the paper that I'm giving here, and also some university lessons on the topic. So some of them are very technical, but they are very good resources if you are interested in learning more. And as I mentioned, you can check on how to fine tune Wave2Vec, for example, with Hugging Face. So there is a link with that. So if you want to use Spark NLP, but you need a different model, at this time, what you can do is fine tune it in Hugging Face, and then you can use a link that I should provide also, that you can migrate the Hugging Face model to Spark NLP. So we have Jupyter notebooks for that. It's not difficult. It's just changing the formats of the saved models, and then you can upload it and create the Spark NLP and use it on your pipelines. Okay, I will also leave here my contact information. If you have any extra question that I was not able to answer, or any additional question, you can contact me at my email or add me at LinkedIn, and that's it. I will check again for the questions. Yeah.
If you have another moment, I see a couple more questions in the Q&A.
Okay, yeah, sure. I have more time. I was just those 3 questions that are remaining there. I can see that some of them oh, okay, there's a new one here. Acronyms are and abbreviations, yes, they are a problem. And if it's possible to mimic the voice of a person speaking in a different language and convert their vocals to English using this model, similar waveforms in speech of the same person. So I believe this is possible. We already have, if I understand correctly your question, we already have those tools that you can speak in your language, and then it will translate to a different language in speaking in the different language, right? So we already have this kind of translators that usually people use it during when they are making tourism in a different country, and they don't know how to speak their language, so they can use this kind of tool. They already exist, so it's basically speech to speech. So it's a translation from one language to another, and it will be a different type of model. But yes, it will also be, it will probably be called automatic speech translation or automatic translation or speech translation. But yes, it's in the same domain and it's possible to do that. How can we keep up to date with model updates? Well, this is a very good question. Usually all of those model updates, they are shared uh, in research papers. So you can follow uh, different congresses or different research events to check, or journals to check for new models. But if you are not part of the research community, those models, they will probably be released on Hugging Face, on TensorFlow Hub, on Spark NLP. So when we add a new model in Spark NLP, we have them mentioned in the release notes. So we say every new model that we implemented. But Hugging Face should also have something similar, and you can always check their website for newer models.
All right, do we have any other final questions for David? If not, I'm going to go back on audio, or video rather, and thank you, David, for the presentation. It was quite interesting. I will apologize once again for the time confusion. I think it had to do with the time zone shift in the United States versus the rest of the world. That's unfortunate. But as I mentioned, I will post a video probably within a few hours of this presentation to the YouTube channel. I put back on the screen the middle portion there, the address you can go to for the YouTube channel where this presentation will be posted, as well as my own contact information. If you would like to give a talk at a future meetup, that would be cool. I am personally located near Washington, D.C., and if you're interested in doing an in-person hybrid, that is in-person with remote participation in Washington, D.C., New York, or Boston, that is definitely a possibility. I just need to find a venue. In any case, for online only or for in-person hybrid, send me a note or message me through the meetup platform. And then once again, we have a next program scheduled for a couple of weeks from now. I think that maybe the rest of the world in the United States will be more aligned with time zones in a couple of weeks, so that there won't be so much confusion. But again, that's with Niels Reimers from Cohere.ai, and I hope that people can join us. The same meetup groups where today's program was posted should all be posted with the program for 2 weeks from now. So once again, thank you very much for speaking, and to everyone who's attending, thank you for attending, and see you next time, I hope.